All right, so here's what we're going to do. We're going to take times. The population showed a mild right-hand skew. But then all of those X bars, the samples themselves fit the population, which means the X bars were all about the same. Okay? Okay. We're going to do one more group here. If we do the Hollywood movie budgets. How would you describe the population for the Hollywood movie budgets? Right skewed? I agree. All right. And again, let's take a sample of 10. And when we look at those samples of 10, they're kind of all over the place, right? They're not very predictable. Like, in particular, I like watching the mean of those budgets for samples of size 10. Look how much they jump around. They're all over the place. Is everybody with me? So it's not very predictable when my sample size is 10. And in fact, if I take a bunch of those, and I asked you guys to describe the shape of these X bars, what would you say?
Right skewed.
Definitely right skewed. And again, I'm just going to go kind of up and down the graph here. You can see how right skewed they can get. Okay? But if I put my sample size up to 25, and generate a bunch of samples. Now looking at those samples, they're starting to be way more predictable. Not great, but they're definitely more predictable. Okay? And if I take about 1,000 samples a couple of times, maybe, like I look at that, do you guys see still a small right-hand skew, but like barely? So if I call that barely right skewed, would you be comfortable with that? And if I jump my sample size up to 50 and generate a bunch of samples, and I start moving around, they don't move around nearly as much. They're a lot more consistent because the sample resembles the population better. Is this okay? Is the sample itself normal? Like when you look at these samples, are these normally distributed? It's the X bars. Now, do these look about normal now? Yeah. Okay. So, all right. So, I'll let you guys get, because I was kind of keeping pace while we were doing this, okay? I never did it with 25. it was going to be very mildly right skewed.
Should we write that in?
Sure. So, as we look at this, y'all, under what conditions was that sampling distribution normal? Go ahead. Okay, so it was definitely going to be normal with a large sample size. Okay? However, was it always necessary that we had a large sample size? No, and in fact, if you look at, say, this one, we did not have a large sample size. At n equals 10, it was still approximately normal. Well, why was that? Well, my initial population had the tiniest amount of skew, okay? So it's either a large sample size or I'm going to call it a well-behaved population. In other words, your population isn't majorly skewed or anything, okay? So under what circumstances will the xbars be normal? So, like, remember, the p hats were normal if np and n1 minus p were greater than or equal to 10. This is going to sound silly, guys, but why can't I use just the same rules here? For starters, we're not talking about p hats. Second of all, you don't have a p without p hats. You guys see what I'm saying? Okay, so we have a different set of rules. That's the biggest difference between what we were doing before and what we were doing after. Okay, different set of rules. The rules go like this. If we know that the population from which we are sampling is approximately normal or symmetric, that's what I mean when I say well-behaved. Okay? So if I know enough about the population, like it's a normal or symmetric population, then the xbars are still going to be normal. Okay? Or as long as my sample size is large enough. Now, underneath some of your faces right now, behind your eyes, some of you are wondering, Ms. Meister, you didn't say how large was large enough. Does anybody want to guess our rule of thumb? Here's a hint. The answer is not 50. Well, 10 definitely didn't work, right? Like when you look at, you with me? And 25 was starting to work for that right skewed distribution, right? So the answer is 30. It was a little bit more than that 25. Okay, so if your sample size is 30 or higher, you're allowed to assume that the xbars will be approximately normal. That will come back to when you guys are doing your project for this particular unit. And I was like, and I asked you, how big a sample should you take? What's your answer going to be? In order for us to use the normal calculations that you're going to need to use, we need at least 30. Okay? All right. So let's look at this next bottom set of examples here. The height of young women follows a normal distribution with a mean of 64.5 and a standard deviation of 2.5. Okay. These are describing my population. So if I randomly select a singular young woman, what's the probability she's 66.5? Have I taken a sample yet? No, so I don't need to worry about any of these rules so far. Because I'm not talking about a sample, I'm talking about an individual. All right. How do I answer that? Well, because the population is normally distributed, we can just sketch our normal curve, label our mean and standard deviation, and we're basically finding the probability that the individual is greater than or equal to 66.5. And then how do I find this answer, y'all? Do these pictures look kind of familiar? What do I do in my calculator?
Normal CDF.
Normal CDF. My guess is it's somewhere between 19 and 22%.
92%.
Is it 0.22? Seem reasonable? All right. So now let's say I take a simple random sample of 10 people, 10 young women. All right. Because my population was normal, the xbars are going to be normal. It's worth noting, again, on the red graph, we're talking about the population as a whole, individual people, whereas on the orange graph, we're talking about xbars, okay? Now, it turns out that the mean of the xbars is equal to the mean of the individuals. Help me out with my standard deviation, though. How is that going to change? How do we find the standard deviation? It's the original population standard deviation, so 2.5, divided by the square root of 10. And I know this because essentially we're finding the probability that a mean is greater than 66.5. Now, this is going to be a much, much lower probability. What are you guys getting? 0.8?
Yeah.
0.08? You did 66.5 or higher? Oh, for this. Got it. That would make sense. 0.8 for the standard deviation makes total sense. Okay. And then if I do that mean 66.5 or higher and put that into normal CDF, now is where we're going to get the much smaller answer. Sorry, guys. That was on me in terms of bad communication. No, 64.5 is in the middle. Did anybody put this into the normal CDF? Or can someone put this in a normal CDF?
I got 0.0062. Oh.
Can you not just put in 0.8 for that?
You can. I assumed that 0.8 was a rounded number. 0.006. It's gonna really, really tiny. Is this okay? Is this making sort of sense? All right, I'm going to jump down to this plumber problem that we've already talked about a little bit. We're going to talk about it a little bit more. Okay? So, again, we had that the population mean was 46,700. The population standard deviation was 5,600, and we're taking a sample size of 42. Okay. So, remember, we basically have done a lot with this kind of like shape center spread, right? The only difference now is that we already have found that the mean of all those xbars is going to be 46,700. The standard deviation of those xbars is 5,600 over the square root of 42, which was 864.10, I think. I'm pretty sure that's right. Okay? Now, remember, our rules for will it be approximately normal were either I knew I was sampling from a normal population. Do we know we're sampling from a normal population here? What do you think? I don't think it's, we haven't been told that anywhere, right? Now, our other option was that our sample size was greater than or equal to 30. Is our sample size greater than or equal to 30? So we still do have that the distribution is approximately normal. So now, here's what we know about our xbars. Approximately normal with a mean of 46,700. Standard deviation of 864.10. Okay. Now, let's say I take my sample. What's the probability that the mean salary is less than $44,000? And $44,000 is to the left of the mean. So the probability it's less than means I'm going to shade less than. And this is just a normal CDF question. Yeah, because that's what the question is. And that's why it's 44. What are we getting? I would imagine that it's relatively small. Okay, so from normal CDF, when you plug that in, we essentially get that the answer is 0.00089. If you wrote that as 8.9 times 10 to the negative fourth, I'd accept that too. That's fine. It's the same answer. Okay. So I think what I'd like you guys to do is, with a partner, try this Yankee Candle question. If neither of you have a calculator, that might be a tough partnership.
Oh wait, I have a calculator.
No, that's something else. I realized I was supposed to be something.
If you shade it to like kind of offset the graph when you're doing the CDF, then your lower is gonna be like but if you shade it like on the upper part and towards the right, it'll be this will be the bigger number and then whatever.
9 hours. So 9 would be your
Oh, M is I said M is 10. I started with M.
Hey guys, did I mess with you on this one?
No.
Does anybody think I'm trying to mess with you on this one?
I just have not been able to pay attention today, so I'm kind of lost. I've been really trying.
Here's a hint. I am trying to mess with you on this one. You're welcome. Hey, did I put you...
I'd say the likelihood is greater than 50%. Considering its average time is 10, so what's the probability that it burns more than 9? And if it's on average hitting 10 hours, I'm going to assume it's like almost guaranteed that it's going to hit 9 hours.
Is that 10? No, so that's 0. Let's check that for a second.
It's like it's these
Yeah.
we'll tell it because this one
Okay, and then what is the probability of the average burning time for those 5 randomly selected samples? So I think you just change it to not negative. Because it's saying
Yeah,
the
it's going to be like basically like 97%. It's my guess.
oh no, we use the 5 number when we do that little thing, but we use 9.
All right, ladies and gentlemen, real quick. As you go to do the first one, which was meant to be a basic question unless you read it really carefully. 9 hours, or I'm sorry, 10 hours, 35 minutes. Do you guys understand what I am saying here? So the first trick is that your mean and your standard deviation need to have the same unit. So you really need, what you needed to do is say that the mean was 600 minutes. And then do that your standard deviation was 35 minutes. Either that or work the other way and turn that 35 minutes into like... So now 9 hours is 540 minutes and you're shading to the right. Do you guys see what I'm saying there? The fact that your mean and your standard deviation were in different units is kind of an important idea. And I told you I was trying to trick you. That's how.
I was only 2% off. That's my educated guess. I was trying to figure out the conversion of the fact that an hour is 60 minutes to making that in like a decimal like the points on that. That's fine.
All right, so for that first one,
We have to choose
5.5 e to the negative 50. No, that's not Great. No, that's not the
The only time I didn't like needles is when I was getting my blood drawn and I could hear it when they switched like tags. Like just like switch things. I was like, I don't want to hear my blood.
are we good on part A? Once you're good on part A, you can move on to part B if you haven't done so already. Yeah.
So we got 5.53 to the like negative 50.
Tell me what you put into normal CDF.
So we did.
Still the same.
So what we did was really funny actually. You pressed the wrong one. I'm sorry.
I'm answering their question, then I'll be over there, okay?
Okay, we put in. Okay, so what we did was we did 540 as our lower, and then our upper was like the infinity 1,000, and then we had 0 for our little thing, and then 35 for our little.
So your mean should be 600.
Okay.
Because this is not a 0 and 1 situation. Like, let your like you only use that, so far we use that when we were talking about Z. Not an individual value. Okay, remember we calculated that Z-score, we turned that individual value, we turned the mean into, that's why.
I totally know what I'm doing right now.
Do you?
Totally. To me, right now, it's exactly the same problem, just that I know that N is a different thing.
So now I've got a sample size of 5, so my standard deviation is going to decrease by divided by the square root of 5.
Okay. Oh, that was saying okay to myself. Let's go. 99.9% sure these candles.
But they should last a real long time.
Now that I've like actually had to do it on myself, I
That's-
feel like
It's almost like that's why I made you guys do it by yourself.
yeah.
It's very likely that your sample will last more than 9 hours. Not 100%, but pretty darn close. I'd put a lot of money on it, let's put it that way, if I were a gambler. All right. Real quick, why don't you guys, same partners, do part A of this question, and if you get part A, let's get to the point we got part A good, and then from there we can do part B.
Oh wait, it's this part. I know.
Standard deviation.
So
Hate this. Why does math have to be so hard?
Because it's our goal to make you miserable.
No, in the center. No, that's not the shape. The center is M,
The part A dot,
which is the mean,
I think.
which is 7.2. What's the probability of that?
Oh no, part A is not done.
And then you need to
I have to do the full divide by the sizes of the sample. The samples aren't perfect, so maybe if I mess it up, I get to say samples are perfect, and that's why I messed it
Yeah, but
up.
I don't think that's
No.
Okay. It was worth a try.
When's the quarter over?
the sample.
Oh, in like 2 weeks, I think. It's either 2 weeks or 3 weeks.
It's 3 weeks because we have a Spanish project that we're starting tomorrow that we have 3 weeks to work on. We have to make a music video.
So 20 to 20, 20 to 20
Oh, wait.
is less than 30.
How am I doing so far?
So yeah.
Yes.
Is everybody good?
Yeah, see, it's 6.
We did this little graph thing for like part B.
Oh, yeah, that's right.
That has to go.
All right.
This.
And then the mean of the X bars, hopefully you guys got 70.2. The standard deviation of the X bars, hopefully you did 2.5 divided by the square root of 60, 2.51.
I got 0.32.
Thank you.
So I did do it right. Once I realized that I did it wrong.
0.32, yeah? All right. How are we doing so far?
We did A. I don't know.
How to do, all right, so hold on. Did you do B and you don't like your answer?
No, I just don't like that there's two numbers.
Oh, got it. Cool. Cool. All right. Now, for part B, we just said all of those X bars are normally distributed with a mean of 70.2 and a standard deviation of 0.32, yes? Okay? And if my height is between 62 and 67, which, by the way, are both to the left of 70.2, I'm only shading that region in the 62 and the 67. I don't want you to put this in yet. Are my lower and my upper. Before we do any of this, should this, not just looking at the picture, but also looking at the standard deviation, okay? How many standard deviations below the mean is this 67? Well, what's the distance between 67 and 70.2? 3.2. How many standard deviations is 3.2? 10, wrong power of 10. It is 10 standard deviations below the mean. Should we get a high probability for this section?
No.
We should get an incredibly small probability, okay? But when we put this, so we're going to put this in as our lower, this in as our upper, okay? And it's just going to be a really, really tiny probability.
Showing up as a 0.
If it shows, I would not be shocked if it showed up as actually 0. But when you guys think about it, getting a sample, getting one person with a height of between 62 and 67 is like less than 1%. Okay? So getting a sample of 60 people where that happens is unheard of. It's not going to happen. And it be a random sample. Okay? How are we feeling about means? Is this okay?